declaration of the EM. You can kind of see what it does. You're going to code up an example just like this. I'm not going to give you this code, but if you want to scroll through and look at the reporting and all of that, that's all fine. Basically, you know the updates, when you're supposed to be implementing, and I'm just going to have you do something a little bit more sophisticated than what I'm demonstrating today. Let's see this just a little bit better. After we run through this example, I want to begin our discussion on evaluating estimators. And you've kind of been doing it on the current homework, where you're comparing estimators, looking at various attributes of estimators. We're going to formalize all of that. And so we don't need to be formal to do it, but I think formalizations make us be able to compare a little bit better. So we'll try to understand what all the theory and decision theory is all about. So we'll be covering that. Here's my example that I'm going to play around with in the code. It's going to be a two-component finite mixture model. So cap K is equal to 2 right here. I'm going to have 2 Gaussian modes in here. In general, we would need to estimate the variance in all of this. I'm going to simplify everything in my code, and I'm going to just say the variances are known. So I'm not going to have my variance updates in there. And I'm also going to let the variances be the same. So in my code. So I'm just picking that to be the variance is 1, and this is the variance is 1. And so I could have added another line of code in here and update the variances if I didn't know them. So in a real example, you won't know them. And so I'll just focus on kind of the basics of EM. So I'm going to get rid of the variance updates, but in your code, you're going to have the variance updates. So what my code's going to do is it's going to compute these probabilities, these pi I k's right here, and this is going to go for k, it's going to be 1 and 2. Since cap k is 2 in my example. So I'll compute all of those probabilities. And then I'm going to use those probabilities to update the means and everything. And so keep in mind, when we're computing these probabilities, we have all of our pi k's from the previous step. We're going to be using those. And we have all of our mu k's from the previous step. The variances, we're just going to plug in right here. And we'll know what those are. So these are going to be fixed and constant throughout everything. So the hands of the statistical gods have been kind to me, and they told me what the variance was. In real life, that never actually happens. So I always have to estimate those. So these probabilities come from Bayes' theorem. So again, all these are just the normal evaluations for each xi. I'm going to look at this density. I'll just write it down in full load Lauren. So this is going to be 1 for the variance, e to the minus 1/2 xi minus mu k t. This is going to be squared, and I know what my variance is. It's 1, so I'll just write that down right there. And so it's going to look like this. It's going to be multiplied by pi k in the tth iteration. That's my prior. If you pick this to be a uniform prior and you said I want to be non-informative on this, that is a reasonable thing to do. I'm going to be using my updated pi k's, which are just the averages of these pi I k's. So they're the total class probability. And this will make it so EM converges faster. I will say, when I hear people say everything's going to converge faster, I'm also aware in a multimodal problem, you can get trapped faster as well, and it can make it so you can't get untrapped very easily. So there's always a trade-off in improving the rates of things. And so sometimes you want flexibility, and you don't want things to converge all that fast, because you want to be able to wiggle out of modes. So I'm just throwing that in as just a comment, and that's general about all optimization. So, and then I just normalize everything. E to the minus 1/2, I'll throw in a 1 if you want. Xi minus mu k squared. And I've got my variance right there. So I'm going to sum over these where it's just summing over k, and cap k in my example is 2. Oh, and I need my top. So I just plug those in. So that's just basis theorem to me. If you want to call it something else, I guess that's fine. I like to explain it in bio days. And then I'm going to just update the means. And the means are pretty easy to update. So all I'm going to do is I'm going to look at the mu k's and the t plus first iteration, and those will look like this. Sum of the x i's pi I k's. These are going to be at the t iteration right here. And then I'm going to divide by sum of the pi I k's. T iteration. And this will happen for k is equal to 1 and 2. So there's usually a for loop sitting right here that's going to update all of those means. So these are just weighted averages. That's I goes from 1 to n, I goes from 1 to n, what we're indexing over. So that's what my code does, is it just computes these two steps and just iterates over them. So I've already optimized the Q function. I knew what the Q function is. I did a bunch of math up front, and then I solved everything using Lagrange multipliers, and I came up with these updates. That's what we did in class. So here's my example. So there's my model right here that I wrote down. So I've got these probabilities. The pi's I'm calling p here. There's only one p because the pi 2 weight is 1 minus p. That's what I called it in my code. So I'll have to set those and generate data from it. And that's what I'm doing here. I need to set my views and I need to set my probabilities. I'm going to use that to generate data, and that's the only place that I'll use that in the code, is generating the data. The generation of the data happens here. So I'm basically just flipping a coin with probability p and 1 minus p. If I'm in the first component, then I generate random data, normal data. I did end up putting an input for v right in here to scale everything. I gave the square root of v. It's really just 1. So that just gives me the option to change that if I wanted to. I won't change it today. And then I just shift everything. So I'm just taking a normal 0, 1. That's what rand n is in MATLAB. And then I'm just rescaling it and shifting it. In reality, because v is 1, I'm just shifting it. And so I do the same thing if I'm in component 2, but I shift by mu 2. So I do this n times, and I generate a whole bunch of data, and I store it. This is the slowest way you can do this in MATLAB. But I like just writing it out so you can see what the whole process. If you know how to vectorize your code, you should probably do that if you want to speed it up. And in an example like this, probably not going to make too much of a difference. I plot the data. That's all I'm going to do. So plot, and then I just do these EM steps. And those EM steps are just right here. And so I have some nested for loops. I'm going to compute these probabilities right here. So I'm not actually normalizing it up here. I'm just computing all these probabilities. Then I normalize down here at the end. And I divide by the sum of all those probabilities. I don't compute just one of the probabilities. I compute both of them. And I probably should check to make sure that they add to 1, but if I've coded everything up, there's no numerical difficulties, they will add to 1. I will point out, my code is already a little bit unstable the way I've written it. And if you're so inclined, you can write it out like this as well, but I have this exponential function in my code. And you should be aware that if these two things are far apart from each other, so if my initialization on the mu k's or something like that is very far from the data, once I square it, that will be big. Once I exponentiate a negative of that, that's going to be very small. These could be zeros. The computer might misunderstand all of that. So every time I see this, I kind of panic in code, and I think I should be operating on a log scale. And so that would be good practice. If you have good, judicious starting values, this will work. And it'll work in my case, because I'm going to have decent starting values on everything. We should probably look at how I pick my initial values. I pick them randomly. I just pick it to be in my space, however big I am. Rand is just a uniform. So I'm just grabbing a value between 0 and n for arbitrary reasons. And I'm just making it random. So I'm just picking some number in there randomly. So my code runs a little bit differently every single time. My probability for P, I initialize that randomly as well. So I don't really have good judicious starting values for this. If you guys know about k-means, and maybe we can discuss it a little bit later, probably a good idea for this algorithm is run k-means. And in fact, because my variances are both the same, k-means is in some ways giving me a solution that's equivalent to the EM algorithm. If I had different variances, k-means and this algorithm would disagree with each other. Maybe you understand that already. I can explain that a little bit more later. But if you did have a k-means algorithm, different variances, maybe this was in a high dimensional space or something like that, those could provide good initial values. And so I might plug those in to the EM algorithm. Right here, I'm just picking everything willy-nilly, just randomly. But I'm picking at least stuff that's like within some maybe reasonable range. So I've got some number of iterations that I'm going to run this for. I will point out, you're going to want to check convergence. So again, this stuff is converging, and so you probably want to include like a tolerance on things. You're probably going to compare your updates on the means or the variances and the variances. You can build norms however you want, and check the t plus first iteration and compare it to the tth iteration. And if those are really close to each other, then maybe it's converged. So that's called Cauchy convergence. So if you're just checking the tail behavior of everything. So my updates on Muse, same sort of thing. I'm just taking this weighted average. And again, this is probably the slowest way you could write this, where I initialize my mu to 0, and then I just keep iterating over this thing and recursing over it and updating my Muse. So again, if you know anything about vectorized code or something like that, I probably should just put some in here. So, but I want it to just look like maybe the way you would learn it if you took an initial C class or a Fortran class, the way they used to code stuff up. Slowly. And then I just include a pause statement in here just to slow it down so we can examine what's happening, and I print everything out to the screen. I will point out, again, this is about the slowest thing you can do on the computer, is at every step, pause and print, or update a figure. So usually, my old code that I presented to you guys, I would check every like maybe 100th iteration and then print it to screen. It's usually something we do in the debugging phase. Okay, so let's just run this thing. I've got some values that I plugged in up here. So mu1 is 2, mu2 is 20, and p true is 0.3. So 1 minus p is 0.7. So I'm just going to iterate over those steps. It's going to run. There's my data. These are my updated values that I'm getting. So they just keep updating. It's like 20 and 2, and the probability is 0.7 and 0.3. Okay. So pretty close. It worked well. So it did what it was supposed to do. It's no big deal. Kind of like that. Let's run it again. Modes are pretty well separated. So I've got 2 and 20, and 0.3 and 0.7 about. Did anything change? So I've got 2 and 20. So this is 2, and that's 20. So let's do it again. See if anything changes. Now it's 20 and 2. So this one was 2 and that one's 20. So you see what's happening is that it's flipping these around. Now if I started with the same initial values on everything and I set the seed, and so it was generating pseudo-random numbers exactly the same every single time, I'd get the same answer every single time, but my code is randomized. And so this is a phenomenon that's called label switching. So it doesn't know what I've called compartment 1 and compartment 2 in the vector that I'm storing everything in. So it starts converging, and it gets sucked into these different modes. One of them starts tracking one of the modes, and the other one tracks the other mode, but there's no obligation for whatever I've called these components, my code to figure out that in exactly the same order. And so you need to be a little bit careful when you're running simulation studies to make sure you've identified your modes properly. And so if I were trying to check to see if this was right, and I compared my answers to the truth, and I was comparing this to 2 and that to 20, I would think there's a huge error. And if I just didn't handle that in my code and figure out what was what, you're going to make mistakes. There's no theoretical correction to label switching problems. What I usually do in a simulation study to control this phenomena, and students always come back to me every time I give them clustering type assignments, and they're like, it keeps changing the labels on everything, and I don't know how to handle that. And so either you know what the modes are and you label them, and you go through after and you say, oh, I better make the switch right here. But that's kind of time consuming on a human's part. So we don't want to do that. What I usually do is I grab a point from each one of the modes that are well separated from each other, and I end up forcing that into one of the components and forcing another point from another mode into one of the other components. And so I end up automatically labeling it that way. And so I cheat, is essentially what it is. But it's a simulation study, and a simulation study, you can control certain aspects of things. So I grab a point that's pretty well separated from the other point. What you could also do is once it starts converging, and the probabilities of certain points are high. So if I got a probability for this particular mode right here that was close to 1, and probably things on the left-hand side of that would have probabilities pretty close to 1, then I use that to label which one of my modes are. So again, I cheat and I control that in the simulation study. So it's kind of a pain to deal with, how you deal with label switching in your own code, but that's how I deal with it in my code. So I anchor it. And so when I say I know what the anchors are, and I know there's some point that's well separated. And so if I were doing this in a real application and I didn't know the answers, then I would have to take far apart points that kept showing up in certain clusters and anchor them and label them to be particular modes. So hopefully that makes some sense. If you can't do that, hand label it. If you start figuring out what your mind is doing when you're hand labeling it, try to implement that. Okay. So this worked really well. The modes are pretty well separated right here. So let's just play around with some values. So maybe I can make this a little bit closer. So I'll make that 2 and 4. So there's some reasonable amount of overlap here. They're still pretty distinct and separated. Let's run this again. This is what the data looks like. That's coming from a 2-component normal. So the variances are 1, and so 2 variances, or 2 SDs, if you'd like, is 2, and the distance between these 2 modes is 2. So I have overlap in both directions. And so it's creating that. And these are probably more common things that end up happening. And so sometimes I see data where I look at it and I say, it's not normal, I don't know what it is. And what I'll usually do with weird data, and I don't know what its distribution is, a lot of times I'll use a Gaussian mixture to represent it. So Gaussian mixtures can represent skewed distributions or all kinds of weird distributions, depending on what cap K is. So they're quite flexible. And so I could have distributions that don't look multimodal, but maybe something like this. And I don't know what that is. So maybe there's a little bump in there. But I could maybe use a whole bunch of normals to represent this. My picture is okay. If I superimpose all of these, it might look like that smooth line. So finite Gaussian mixture models are very useful in just representing distributions that you don't know what they are. They don't have to be well separated modes. So this is kind of an example of that. And so if I asked you to eyeball this, so I should go back to the other example, what you could have done in those well separated modes, if somebody could have come in this 1D example and said, I don't need probabilities on all of this. I can see what's in each mode. There's nothing in this gap between it. There's really almost no uncertainty in anything. The probabilities are close to ones and zeros if the modes are really well separated. In this case, the probabilities are not ones and zeros because I have so much overlap in here. And so you can see this, that it doesn't look normal and it also doesn't look bimodal. The big surprise is how well this does. So it still captures those two things. This used to be a hard problem for people. So if you go back to the 80s, mixture models and all of that, estimating them used to be a really intensive process. What we're doing right here, people would debate the methodology, and now it's kind of an easy problem. So we give it to people for homework. So this used to be a whole research field for people. They would study this phenomenon, what are the best techniques for estimating mixtures. EM turned out to be one of the big contenders. There are other ways to do this. So let's look at another example. Let's make these even closer to each other. So I'll make that 3. See how well I do. So a little bit off. So kind of close, 2.3 and 3.1, but if you're looking at the decimal places of things, this is a little bit farther away from my old answer, and it's because it's hard to discern these two modes. And it's getting harder and harder. So there's so much overlap, and there's probabilities in here in the middle that are close to like 0.5. And it doesn't really know. And so I'm uncertain about things, and so that shows up in my estimates. The surprising part is how well this still works. So it's kind of amazing. Let's do it again. Make it a little bit closer. So 2.5. It's okay. So it's hard to distinguish these two numbers. I got 2.3 and 2.3. So can't really tell anymore. But I think that kind of makes sense. Those modes are getting really close to each other, and it has no idea. So if I look at these probabilities also, they've got a little bit whacked too. I've got 0.8 and 0.2, where the real numbers are 0.3 and 0.7. Let's put these right on top of each other. So now I'm going to make a big mistake, and I've got data that's coming from a one-component model. And I'm trying to estimate it with two-component model. I've got these probabilities right in here, but I've got these modes that are stacked right on top of each other. You can't actually discern them. So let's run it again. See what it does. These numbers are turning out pretty good. Those are converging close to 2. If I look at my numbers right here, I've got 0.6 and 0.35. Actually not too bad, kind of surprisingly decent. Let's run it again. Okay, this is a little bit better. I was really surprised about 0.65 and 0.35. This looks better to me. So it's getting that. It knows that the centers are 2. It's not hard to figure that out. This actually is a Gaussian distribution. But the probabilities are really just crazy. They don't have anything to do with what I inputted. And it turns out I don't converge to any old number. So there's all kinds of ridges in this likelihood function that we've just created. There's a flat space. And so, and there's a big ridge on the probability for P that's flat. What that means is that you can't identify the P's. So there's no actual modality to them. And so when I have ridges in my space, or the function takes on the same value in terms of the parameters, that's called unidentifiability. And so in this case, P is unidentifiable. So I'll point out there's a QE question that I periodically ask, and it looks just like this problem, except I changed something in here. I'm not saying I'm going to ask this year. I've asked it many times. A lot of people mess this part up. But I'll do something like this where I'll say, let xi's be a mixture between pi1 and a binomial. And I'll say I've got n1 and p1 plus pi2, a binomial, with n2 and p2. I think I end up asking the question like this, where I'm making n's the same. I could have changed them. And if n is big, there's big separations between these two things. So the expected value is n times p2 right here for this mode. The expected value is n times p1 for that mode. And if the p1s and p2s are very different, these will be pretty separated from each other. I ask you to try to estimate this model. And a lot of people do exactly the right thing and they employ EM on it. They tell me all the steps. And then I usually ask a question about this, right here. What if this was 1? So these are really Bernoullis. That's an interesting question. So all I'm seeing, if I ended up letting n be big, I would end up seeing values. So let's just make up some values. Let's make P1 and P2, I'll say 0.1 and 0.9. And I'll say n is 10, just to make the math easy. So if I sample from mode 1, I'm going to end up seeing 10 times 0.1, so I usually see about 1 success. But in the other mode, I end up seeing usually draws that look like they're around 9. So I see draws that look like they're around 1, or draws that look like 9. So I'd end up getting this data set where it's like you can kind of see the mode now. So I've got a lot of stuff around 1, a lot of stuff around 9, no problem. But if I ended up making the ends 1, if I sample from this mode right here, I'm going to see something that looks like either a 1 or a 0. And if I sample from this mode, I see a 1 or a 0. It's very hard to distinguish those two things. Which one did it come from? So if I showed you a 1 or a 0 and I asked you which mode did it come from, you wouldn't have any idea. And I think that that just kind of makes sense. All you can estimate in this model this is where n is equal to 1 for the binomial case, so really just Bernoulli's. I can only estimate this parameter, p1 plus pi2 p2. So I'll call this p squared. So you can only estimate this function right here. So if you did run EM on this problem where these are just both 1s, you would converge to some p's and pi1, pi2s that would be converging to this number right here. And so in my case, if this was a point, if this was whatever the mixture weight was, whatever this number is right here, basically I could model that same sequence of 1s and 0s using a Bernoulli with this total probability. And so modeling this mixture would be identical to modeling a Bernoulli with parameter p tilde. And so this would end up being equivalent to that. So you can't identify all these parameters. Instead, all you can do is identify this function of the parameters. And so if you did write down the likelihood function for this model right here, you'd see a big ridge that runs through this function. Right here, it would be flat. So these would all provide any number on this ridge right here. So if I change P1 and P2, and I can do that in an infinite number of ways and compensate with pi1 and pi2, and come up with the same number. So let's say this was like 0.7. There's an infinite number of ways that I can juggle around these 3 numbers. I say 3 because that's 1 minus pi1. There's no degree of freedom. There's a constrained degree of freedom there. And so there's an infinite number of ways of moving around these 3 numbers and coming up with something like 0.7. And so if you do write out the likelihood function and study that likelihood function, you'll see that there's a ridge right there. And that's called unidentifiability. If the modes, like in this example right here, if I did something back to my normal example and I made this like 2.1, so they're really close to each other, there's a lot of overlap because the standard deviation is 1 on both models. This is what we call weak identifiability. It's almost unidentifiable. And so there's almost a flat section on the likelihood. There is a little bit of curvature, and that's going to make it so our optimization scheme doesn't like converge to the right thing very well. So I will point out that this likelihood function is multivariate. So it does give you some difficulties. So if I rerun that right there, I come up with astonishingly decent numbers. Let me just do this. Let me make it even weaker identifiability. I'm going to change the variance to 10. So still works okay. Oh, gets me to 2. Can't really distinguish these two things. It's giving me exactly the same values right there. I'll run it one more time. These probabilities aren't converging to the right probabilities right here. And these numbers look like they're exactly the same twice in a row. Even though there is separation, that surface is so flat that the algorithm is having a hard time picking up on where the actual mode is. And so ultimately, if I had data that looked like this, if it was coming out of a 2-component mixture model, I wouldn't be able to figure that out. And no algorithm would. This problem gets worse in high-dimensional space because high-dimensional space is sparser and you need more data to fill it in. And so if n data points are sufficient for estimating everything really well in a 1-dimensional space, if I move to a 2-dimensional space, so if these clusters weren't just on the real number line, but they were out there in a 2-dimensional surface, I would need n² numbers to be just as competitive with that. So to have the same sort of asymptotic efficiency of everything. We'll talk about that term later on. So the efficiency of my algorithm, but also the efficiency of my estimates. And so if I move to 3-dimensional space, I would need n³ data points to be just as precise in my estimates as I was in the 1-dimensional case with just n data points.
How do you initialize each of your P's?
I just picked it to be random. So in my code, it's all right here. So I pick it to just be rand uniform. And that's why it's converging differently every single time. And so I wanted that so that we could see that it converges differently if there's weak identifiability or non-identifiability. And also there's some label switching issues. So all things you need to think about. Any questions about all that? Okay. So homework is up for you. Practice that. Shouldn't take too long to code it up. But I would say get started on that. This shouldn't be as intense as the other simulation study. Okay. If you guys are ready, I'm ready to move gears. Cool. Let's start on evaluating estimators. I'll probably say a bunch of stuff that you guys already know today. And we'll build this up and I'll hopefully say a bunch of stuff that you haven't learned already. Evaluating estimators. I'm just going to jump right into it. Usually people start with loss functions. They tell you all about loss functions. And then they tell you about risk functions. I'm going to do it all together. So for risk, this function is usually what we use when we're comparing different estimators to each other, when we compare the performance of various estimators. So the risk function is going to look like this. Expected value. There's going to be some function in here. It's called a loss function, and I'll tell you what that is in a second. I'm going to change my notation a little bit from what I've been using. But this right here is what we call an estimator. So the idea is this function right here, EX, is what I've been calling usually theta hat. It's a function that takes in the data and produces an estimate of theta. And that's what we want to do, is estimate theta in our model. And so this could be high dimensional, but I'm just going to write it down as though it's a scalar. But everything carries over to high dimensional space, and everything I've written down. So this function right here is referred to as a loss function. And what loss functions do is they take our estimate of theta, and it's going to map everything to some positive number. So loss functions take on some positive number. So this is an expectation of some positive thing. The expectation is over X. So our data space right here. So I don't actually have data that I'm plugging in here. I'm thinking about over a distribution of data and what that data looks like. Keep in mind, the data that I generate, I need theta to do it, to generate the data in the first place. And so what this is it's an averaging over the different data that I might get from some sampling distribution X given theta. So I'm averaging over, and I'm looking at how this estimator compares to true theta, where the data is being averaged over, right here. So this looks like this. So I'll just write it out in full blown glory. This is my loss function. I should say 0 is good. This is bad. So it's going to measure basically the difference in some sense. We'll have to discuss that term, difference. I don't necessarily just mean subtraction. So the disparity between theta hat and theta. If they're exactly the same, I should call that 0. There's no loss incurred. So I'm not going to penalize myself for getting a correct answer. And this could go really big. So this would start to, obviously we're never going to get an infinity, but if we got something really big, it means that my estimates are going to be really different from the truth. So this is just going to be this loss function right here, and I'm going to integrate over the data space. dx. So, and this is called risk. And usually we denote that as r theta. So keep in mind this is a function over theta. So when I generate the data depends on theta, and my estimates might perform differently for different values of theta. Think about the binomial example that we've already studied. So when p's in the middle of the space, estimates are easy to get. And everybody kind of agrees. So the bootstrap, the delta method, and Bayes, they all probably perform reasonably similarly if n was reasonably large. So probably even for like 10 or 15, they're all really competitive. But near the boundaries, they perform differently. So that's what this is saying, is that we need to account for where you are in theta space, how you've generated the data, and we have to consider how much expected loss. So I'll just, this risk function is really just expected loss. They're synonyms. That's exactly what it is. But this risk function is going to account for different values of theta. So if you think about this a little bit, when I see this equation, I think simulation study. And this is always what we're comparing in a simulation study. What we're doing is we're generating a data set. So I get something out of here, I plug it into whatever my estimation technique is, and then I look at how disparate it is from the truth. In my simulation study, I've generated data under certain parameter settings, and where I always use that in my code is in my comparison. I don't use it in my estimate. If I needed the truth to build my estimator, what are we all doing here? You know, if You told me the truth already. I don't need statistics. So what this is telling us is, on average, if I just keep popping out data sets out of here, cap x, and I plug it into this, and I compare this thing, and I'm averaging with respect to how often that data set happens in the first place, and I just average over it, that's what this is, right here. So let me give you an example. Let's talk about the L2 loss function. But basically, all simulation studies are coming up with some criterion to make a comparison. You get data out over and over and over again. This integral is over all of x. And what we usually do in a simulation study is we say how many iterations we want to run over it. And we want it to be sufficient enough that we're covering that space of x. So if we're not, we need to run our simulations longer. So the L2 loss function. I hear people talk about this all the time. So this is going to look like this. E to the x, ex minus theta squared. And that's what it is. So you always play around with this loss function. A lot of people like this loss function because the squaring makes everything smooth and we can do calculus. If we were running an actual simulation study, who cares? So we just compute something. If we were trying to solve things analytically and write down mathematical expressions, having smoothness is pretty convenient. So I would say one of the reasons we use this function, this loss function, is because we're lazy and we like convenience. So that might be true today. But think about poor Newton or Fisher or something like that. They couldn't do a big simulation study. They didn't have the computational horsepower to do it. And so they needed to do something. So usually I tend to think this is something that might be convenient. Saying that, if I were looking at things that are coming from a normal distribution, and I do have a relationship between mu and x, that the difference is squared in the exponent, that's kind of a natural loss function to evaluate because it's part of that distribution. So I think that's also part of the reason a lot of people run off to this loss function. So the risk associated L2 loss is just the expected value of this thing. Squared difference. So it's just that. Or integrating over all of x. Some people will call this the MSE, the mean squared error. So that's probably the most common way to compare things that I've ever seen in all of statistics and engineering and everything everybody does. Is they usually look at something like MSE. And what MSE is gauging is the squared difference on average. And so keep in mind, big errors are being penalized very hard because of that squaring. So if you're wrong, you should get penalized harder and harder and harder. That's what this does. That may be a good idea. Sometimes it's not a good idea. So this is called MSE, mean squared error. Usually in a simulation study, when we do this, you replace this expectation with a sum in an average. So an empirical average. So I'll just take all my data sets, I'll plug them into this thing, and I'll just average over them empirically. Take an arithmetic average of this squared difference. The name is supposed to be obvious. So I always read this backwards. This is the error, the discrepancy. I'm squaring it, and then I'm taking the mean. So that's what it is. Let's look at a decomposition that I think most of you are probably familiar with. This is the bias variance decomposition of MSE. And sometimes people will mistakenly say this is the bias variance trade-off. It's just an exemplification of the bias variance trade-off. So let's just write this down. So my L2 risk function MSE is just this, E of x minus theta squared. I'm going to just change my notation a little bit, just to save me some chalk. I'm going to call this theta hat minus theta squared, expected value. I'm going to make a definition. I'm going to, I won't use the definition, I'll just write out the notation for this. This is the same as theta hat minus the expected value of theta hat plus the expected value of theta hat. Keep in mind, the expected value of theta hat, the expectation that I'm taking is over x. It's the only thing in there. So this is over x. This one is over x as well. I probably should write x given theta, because that's what it's really over. But I'm just going to write x on those for right now. Yeah, it's the same thing. Minus theta. So all I've done is I've just added a funny form of 0 in all of this. I'm going to include some braces in here, and I'm going to expand this quadratic. So this will look like this. Expectation, I'll just get rid of the notation denoting which expectation it is. All these expectation operators are the same expectation operators, so they're not different. So this is going to look like theta hat minus expectation of theta hat squared plus 2 times theta hat minus expectation of theta hat times expectation of theta hat minus theta plus the other quadratic term. Expectation of theta hat minus theta squared. I'll close this. Everything is inside of the expectation. So this is going to break up into 3 terms. I'll write them all out. Expectation of theta hat minus expectation of theta hat. Get that square in there. So that's all squared right there. And this is going to be plus 2 times the expectation. I want to just point out, there's no x's in here. So I've already taken an expectation over this. So it's averaging out the x's in here. So this is a constant with respect to this expectation because I've already averaged over everything. So this is going to be expectation of theta hat minus expectation of theta hat. That's sliding over this right here times this expectation. Theta hat minus theta. So when I slid the expectation over this mixed term right here, the expectation only appears on that. Because I've already taken the expectation. I can write down a double expectation here. It's not the same thing as that iterated expectation, because the expectations are over the exact same thing. So if I average over something and I get an answer, and I average over whatever that average answer is, I get that same answer. So it doesn't change anything. So the expectation only slid over that. So, and plus, the expectation of all of this stuff, but there's no, this has already been averaged over right here. And this is fixed, theta. So this expectation, when I hit it into this third term right here, doesn't do anything, because I've already taken the expectation. So that stays exactly the same. So, no surprise, the cross term cancels. This is the 0. So it decomposes into 2 terms. Decomposes into this term and it decomposes into that term, and they get added together. Does anybody recognize this? It's the variance. So it's the variance of theta hat, which is just the variance. I'll go back to the old notation of our estimate, our estimator. So I should distinguish those two terms. An estimator is the function. So it's the function when I don't have data to plug into it and I'm just using a dummy argument. When I plug actual data into it, it's called an estimate. So not a big difference, but a difference worth discussing. So this is the variance. And this right here is the discrepancy between my average and the truth squared. And the discrepancy between the average and the truth is called bias. So that's the definition of bias. So this is the bias associated with theta hat squared, which is just the bias of our estimator. How biased is that thing? So, and we're talking about on average. So how biased is the estimate? Not just for one data set, but averaging over a whole bunch of estimates. And so, a lot of people will call this the bias variance trade-off because you see it in this decomposed form. That the MSE is attributed by one of two things. It's either the stochasticity in the estimate or the systematic bias in the estimate. That's true for any loss function though. That how much it wiggles around and floats around or how much it's systematically biased is the only thing that's gonna bring up the risk, is those two parts. So estimators can only do one of two things. They float around and they're somehow systematically maybe biased. So it's not the case, I think people get confused, that they'll think, I've got some fixed MSE right here, and for a fixed MSE, if I bring down the bias, the variance, then I'm going to need to bring up the, if I bring down the variance, I'm going to need to bring up the bias to compensate for that. Different estimators have different MSEs. So they'll produce different MSEs, and those different MSEs are controlled by one of two things. It's systematic bias or variance. We're going to come back to this discussion next time on Monday. We'll bring in some new loss functions. I'll tell you properties of those loss functions. And I'll tell you how to control these two things. But what I want you to understand in this whole lecture is there's no perfect answer out there. So answers can be good in some certain parts of theta space. And so coming up with answers that are good on average is different from an answer that's good in a particular place in theta, right there. We're going to have to think about all of that. And so there are no just perfect optimal estimators out there. We have to define what that is. So for instance, what I might do is I might say, I want to be in a class of bias estimators. And what that would mean is I want to come up with estimators with the lowest variance. But that's constraining yourself to a particular class of estimators. Let's pick up with that discussion on Monday. Yes, we did, Julia. Otherwise, you're going to give me a job because